maybe not. Let's redraw that very, very quickly. From the centre upwards, 1. And we had that angle there originally that represents the radius. Well, we are going to get rid of that radius as such. You don't have to do that on your diagrams, but you can dot in a new one which represents that line like such. In other words, we've moved that radius, or the radius down from there all the way down to there. Do that in your diagrams very, very quickly. Well, the angle formed between the two is quite self-explanatory. The angle being Jack Glennon. If Jack ain't there, we'll have Rob Davies. Rob Davies ain't there? Well, we'll have Jack Griffiths. 90 degrees, okay? Well done. 90 degrees. If we continue to move that radius around, in that direction, like such, I'm going to get rid of that for our explanation. It's moved around to create two halves of the circle. Well, that circle on either side, or that semicircle on either side, it too has an angle. It ain't 90 degrees anymore, but on this side it is, Daniel Milsom, 180 degrees. And on the other side, the angle is 180 degrees. Do so on your diagrams now. Well, we refer to that as pi, and we refer to that half of the circle as pi as well. Make a note to that effect. If Joe Creed is there, Joe, inform us of the formula now for a circle, or for the circumference or the area of a circle. If Joe Creed isn't there, we'll have Josh. Do it. Think about it, Josh. Okay, if not, Luke Wheeler. Okay, it's a good job Ali's sitting next to you. You should be able to identify that the formula for a circle, or to measure the area of a circle, is now not 1 pi, but, excellent, 2 pi r. Since there's 1 pi, there's 2 pi, and the radius, yeah, you can see, has split the circle into 2. 2 times pi times the radius. But we did say that in SI units, we don't measure in degrees as such, we do measure in radians. So we could say that 2 pi radians, that's 2 pi radians, is equal to what? 360 degrees. 2 pi radians equals 360 degrees. Okay, if I can get rid of them drawings very, very quickly for now, let's clear that. You should have that information already. Let's go back to the value of our radius. There's our centre of our circle. We'll draw the radius up in that direction, and we'll draw it up in that direction like so. And we did say that we didn't know the value of that angle. Well, since there's 2 pi radians in a circle, and since the circle is divided in half by the radius, we can take 1/2 of the circle, like such, into consideration where we want to calculate the radian. Well, you know that value already, which is pi. We know the angle of that half of the circle, which is 180. Do so now on your diagrams. Therefore, we divide one by the other, and we could say, therefore, that a radian is equal to 180 divided by pi. Type that into your calculators very, very quickly, and you should have an answer that represents something in the region of, I'll give you a moment to type it in. .295, or we could round it up to 57.3, and that will equal a radian. Okay, Luke, just describe the formula used to calculate a radian. Well, 180 divided by pi. Okay, let's just clear that. We'll need to move on, so very, very rapidly. With regards to our conductor loop that we demonstrated very, very earlier on in the program, well, if the coil is rotating at n revolutions, then it is said to be rotating at what? We'll take n representing the frequency in this instance. Now, since that conductor loop on the bottom right on the diagram is rotating, it means it's rotating in a circle, 1 revolution. So we could say per revolution, or the frequency, is represented by 360 times n, and whatever the answer is, it's going to be, in this instance, in degrees. However, it is per second. So you can make a note to that effect. If the coil is rotating at n revolutions, then it is said to be rotating at 360 times n degrees per second. Remember, frequency with regards to n, or n equals a frequency in this case. Okay, let's clear that. Let's move on. Right, all the information with regards to an AC waveform, yeah, it can be plotted on a graph. Now, the information that we're concerned with about plotting an AC waveform does consist of, let's have a Jack Griffiths informed me of one of the informations that we're concerned with in plotting an AC waveform. Let's have Rob, if Rob isn't there, Alex, James, Daniel, Josh Tillett, Luke Wheeler, Ali, Ben, Joe, Brad, Jonathan, Josh Lynch, if you're there. Maybe not. Okay, we are concerned with the first bit of information in plotting an AC waveform is, we could say, what we refer to as the maximum voltage or the peak of the waveform, otherwise known as, Ali, amplitude. Well done. Make it up. Amplitude. We also need to consider the cycles per second, which is termed as the frequency. Well done. We also said that it takes time for that conductor loop to rotate, so we are concerned with periodic time. And of course, the maximum voltage or the instantaneous value or voltage, like so. So we've got amplitude, frequency, periodic time, instantaneous value or voltage, maximum voltage, which in the case of our graph that we drew earlier was, Daniel, how much? 1 volt, super. All this information can be represented on a graph, but I will iterate to you now that plotting an AC waveform or a graph can be quite complicated. Firstly, it takes time. Secondly, to determine the accuracy of such a graph, if I ask any one of you to draw the same graph with the information as such, and I ask you to pick a point or a value on that graph, you will have different answers. There are other means and simpler ways of plotting the graph, but however, for this instant in time, we are concerned with all these 4 points and replicating them on a graph of some sort. So therefore, the graph that we're concerned with does look like that. So I will give you a moment to draw it. You might want to stop this video and freeze it at this moment in time.